All right, so let's see. Thermodynamics, page 68. No, 69. Today is February 27th, and this should be lecture or whatever, class 12. All right, so last time you had the exam, okay? So, all right, so you want, let's talk a little bit about the exam, but basically the way I look at it is that exam 1, so you had 3 problems, no? So the last 2 problems, I think this one was from the homework 1. The following one was from the homework 2. Yeah? Okay, so nothing new. The first one was kind of new, but really the material wasn't that new, no? Okay, so if you want, let's maybe do the first problem, since it was new if you want. So let's see, problem 1. That way you have a solution for that one, and for the problems 2 and 3 you can go to the solutions on the homework. So let's see what was, I don't want to give any grade, but basically let's see, this is the problem statement. I don't know who that is, I don't want to show anything, but let's see, this is, I cannot read that good. Let me see if I have one here. Okay, that one doesn't matter. You can see the solution. Can you read it, or it's better if I zoom a little bit? If I zoom a little bit, so basically let's do this one. So for a refrigerator with automatic defrost and top mounted freezer, okay, that's not that important, no? But what's important is that it's a refrigerator. So what is the first thing I will do? Some type of refrigeration cycle. So what do we know is going to happen on the refrigeration cycle? So I just give you, see, the normal notation. I'm not even worrying about anything here. Too hot. And what do we know about a refrigeration cycle? It requires work or power. Okay? So let's see, what do we know next? The annual cost of electricity is $50 per year. So $50 a year would be what? The amount of the power you are putting inside the fridge per year, no? Yeah? Okay. So let's say part A, evaluating electricity at 8 cents per kilowatt hour, determine the refrigerator's annual electricity requirement in kilowatts per kilowatts hour. Okay? So let's see, we know part A if you want. Let's do part A. $0.08 per, what is it, kilowatt hour. Okay, so let's see here, what do we know? We know what is the cost, $55 a year. Okay, now we know that basically what do we know is the amount of power we need to put inside, no, throughout the cycle would be this one, and this, what is the cost of this one? 0.08. Okay, per kilowatt hour. Okay, so what would be the amount of power in kilowatt hour you need to put into the fridge will be, I mean, this is way too thick. I don't know if I can work with. This one might be way too thin, but will be what? The $55, no? I'm solving for this one. Divided by the 0.08 per kilowatt hour. All right? So if you look at it, just by looking at the units, what do you have? The dollar will cancel. This one will go on top. So what will you have over here? Kilowatt hours. Yeah? Which is what they ask you to find in kilowatt hours. So this is equal to 687.5 kilowatts. Okay, so in this problem, what I'm looking for, the first thing that I was looking for is what? Some type of figure, no? That you recognize this is a refrigeration cycle, that you tell me that W is the power. Okay, I know that many other times I know what you mean. Okay, but what I'm trying to teach you is what? A procedure that the equation comes from figures, no? That you show me that you understand the material. So any questions so far? All right. Oh, yes, go ahead.
Why don't we include that it's $55 per year? Why don't we convert years to hours?
If you want, you can do it per year, and then what happens is that this will be, the years will cancel, or this will be the amount of kilowatts you use per year. You see what I mean? Okay. You can keep it. It will not change anything. All right, so part B of this problem. So part B of the problem, if the refrigerator coefficient of performance is 3, determine the amount of energy removed from its refrigerated space annually in megajoules. Okay? So over here, obviously, yes, you need to say, you can call it whatever you want. I think on the classroom we call it beta, no? But again, I know the figure is on the other page, but I'm going to redo it. Okay, so what is the difference between a heat pump cycle or a refrigeration cycle? Is that if we look at it from this side, this is a heat pump, no? If we look from this side, this is a refrigeration. Okay? So, the coefficient of performance, beta is equal to what? What was the general definition? Whatever you get out divided by whatever you need to put in, no? So if it is a refrigeration system, what are we trying to achieve? Pour the cold into the system, no? What do we need to put into it? Work or power. All right? So you see, if you give that equation, I want to see some type of figure to know what is exactly everything. Okay, so over here, what we needed to do is what? We know beta is 3. Okay, so we know beta is 3. And this was equal to what? 687.5 kilowatts hour. So let's see. So how much cold or how much heat can we remove from the system? Will be QC. So then we'll have here QC is equal to what? It's beta times W. Okay? And they ask us to find the result in megajoules. All right, so let's see. We know beta is 3. The W we just calculated is 687.5 kilowatt hour. Okay? Okay, so if we keep doing unit transformation over here, what is 1 joule? Watt per second, no? So I mean, maybe you don't have to put this, but if you want, you can put 1 kilojoules equals 1 kilowatt, no? So this will eliminate the kilowatts. Now we want this in megajoules. So what do we need to do now? Eliminate the kilowatts hours. Yeah. Wait, what do we do here? No, 1 joule. No, it's the other way around. 1 watt is 1 joule per second. Okay? So that means that 1 kilowatt will be 1 kilojoules here per second. Yeah. So now, sorry for that. So we need to do then the 1 hour is what? So 300, 600 seconds will be the 1 hour, no? So this hour will cancel with this one. This second here, sorry for that, that's completely confusing, will cancel with this one. So if you do this calculation, you get that Q sub C is equal to 7,425 megajoules. Okay, so I know this problem, I mean, when you know how to do them, they are very easy, but you need to be very careful with the units, no? You need to follow really what you're doing with the units. So that was basically the only problem that was new to you on the exam. Okay? The other 2 problems, there were the second one, I think we did on the homework, and I don't know if we even did it in class as one of the solutions. I don't know if you asked me to do it, but you know, generally on the exam, I try to give you something that I've seen before. Okay? I don't like to give you something that is completely new, or at least that I know we have mentioned it or talked about it. Okay? Okay, so if you want, I'll give you first my opinion about the exam. It's the same every single semester, so don't feel bad about anything. Is that first exam, generally, there's always, for a few people, it goes very well. For some of the people, it goes more or less, but then there's a bigger majority than for other classes that the exam doesn't go that good at all. Okay? I'm going to tell you the truth, it happens every single semester. I think I've been telling you from day one, what? If you don't come to class with the tables and practice with me to do the problem, what's going to happen? You're going to have a surprise on the first exam, no? And every single semester, everybody looks at me like, oh yeah, sure. Okay? You know, it has been happening every single year, so I know what happens. Okay? So, and I know as well that now, generally, you react, so you see that what I was saying is kind of true, or you say, okay, you know, maybe I need to put some extra work, but then now, generally, you do good on the second exam and the third exam. Okay? So, generally, what I do, and I don't do it for everybody because I try to be fair with everybody, but at the end of the semester, I came up with different percentage for the first exam, second exam, and third exam. Okay? Generally, I leave the third exam, let's say 30%. I think they're all 30%, no? Okay? And then I do another column at the end, okay, to see, okay, what would be the grade if I give just 10% on the first exam and give whatever it would be, 40 on the other one, no? Okay, on the second exam. Okay? And I do those 3 columns and I see what is your best average, and that's generally the one I will take for your final grade. Okay? So So I try to help you. But again, what's very important is that I always say the same sentence is that I don't care about the knowledge you walk into this class the first day, okay? Because that's completely out of my hands, all right? So I cannot judge you on that. But it is my job to judge you the way you're going to walk out of that door the last day of classes, no? Okay? So what's important is not the impression you give me at the beginning of the semester, is the impression you're going to give me at the end of the semester. All right? So generally on the last exam, because generally you don't get it back, I don't really put I don't really put a numerical value, unless you come see me, okay? I generally just put a letter grade, which corresponds to my final impression about you, okay? And then I go back to your grades and I try to put you something to make it work in that direction, okay? All right, so don't get discouraged or anything. I tell you, it's normal. If you didn't do that good on the first exam, I'm not surprised. Okay? I think it's whatever, you know. You need time to learn how to study. Yes?
Does the final have material from the entire semester?
Basically, you will very soon find out that here is not like we do something new, we stop, we do something new, we stop and we do something new. Everything builds up on the previous. So, except maybe for this, the two, like problem 1, this one and problem 2, heat transfer, probably you won't see it anymore, but like the last problem, they're all going to be like that from now on. Okay? For different things, you know. All right, so now I want to have your impression about your exam. Any comment about the exam? Yes. The amount of heat removed from the system. Okay, so let's go. Where is the problem statement here? Okay, so let's see how can I explain this. Okay, I mean, okay, all these problems to me about me is like if they say the amount of heat removed, I agree that's what is on the problem statement, but basically this will not become a refrigeration anymore. It will become a heat pump. No? So I think maybe it's the way the problem is mentioned over here. Is that when you use a refrigeration system, what is the way for you to, if you want, remove the cold or put cold? It's through QC, no? If you look at QH, then you'll be looking at the heat pump cycle. So then, otherwise, how will you do it? Otherwise, what have you done if you did the other one? But QC you found it over here. Now, so you know W, 36 kilowatts per hour, so you need to do other units transformation. Yeah, you could do it. I think if you found QH, I saw some people doing it, I don't think they were penalized, okay? Alright? But basically, if you think about it, maybe it's the way the problem, it's the problem statement. They say here, if the refrigerator coefficient of performance is 3, determine the amount of energy removed from its refrigerated space annually. Okay, so the way I look at it is like, yes, is that how do you? So basically, the way I look at it is this: because it's refrigeration, what is working over here is the Q sub C. Okay, so the amount of heat, the amount of heat you're going to remove should be equal to what? To the amount of cold you're going to put in, no? Okay, that's the way I look at it. But if you did it the other way, I should not take points off because it's a little bit, I see what would be, that would be a logical mistake. Okay? So if you see you did that mistake, maybe come see me so I can recheck your problem. All right, because it has nothing to do with your understanding. It has to do that's the way you understood the problem, and that's fine with me. Okay. All right. So stop me like 10 minutes before the end of the class so I can give you back the exams. Okay? I don't give you now the exams because if I do that, you're going to be spending the rest of the class just looking at your exam. All right? So the way it works is that I give it to you at the end of the class, look at the solutions of the homework, look at this solution, look at your exam, compare it, and then if you have questions, you can come see me, okay? All right, so 71. So did we do a different chapter? Did we add a chapter 2 on the class notes? Let me see. Yes. First principle of thermodynamics for closed system. Okay, so we're going to have a chapter 3. And sorry, this one is very thick, so sorry for that, guys. Let me unzoom this a little bit. So chapter 3. First principle of thermodynamics for, so before we had closed system, this one I like to call it open systems. Okay, so remember that what is called, or what I like to call open system is what they call in many textbooks what? Control volume. Okay, and you will understand now why. Okay, so let's write over here. Let us consider an open system or control volume. Okay, slash control volume. Okay, so this is not a closed, it's not a piston, it's not a closed box, it's something that is open, no? Okay, that's why I like to call it open system, different than the other one, closed, open. Now, why do they like to call this one control volume? Because sometimes what would be the volume of this? I mean, you can make it go inside, but generally this will be the volume. Okay? Something that was specific to the closed system is that the amount of mass inside, the amount of substance inside was always constant, no? The piston could expand, compress, whatever you want, but the amount of substance inside was the same. So what's going to happen on the open system? We might have substance going in function of time. So let's say dm, dt, dm sub I for input dt. This is what is called, since you do not have fluid, it's a bit harder, but we call that m dot, okay? So the dot means in function of time. All right, and here we're gonna have something similar. But for the output. Okay, so Okay, I'm have to redo the figure later, but it's fine. So this is an open system, but you see this is what they call the control volume. Okay? Are we adding any mass over here? We are not adding any mass, no? Nothing's happening. So in most cases, that's what you will generally study in fluids. You can say that what? So m dot is what is called the mass, it's called dm dt, is what is known as the mass flow. Okay? So I think it makes sense to say that the mass flow in should be equal to the amount of mass coming out. Yes.
Are we going to talk about compressible fluids as well? Or are we going to...
Compressible or incompressible?
Because I know that formula.
What do you mean about talking?
Because I know that formula changes if it's a compressible fluid. Sometimes.
No, that one doesn't change.
Okay.
The amount of substance is still the same one. Okay, I mean, we have talked about compressible and non-compressible. What we change is the gamma. Okay?
Oh, okay.
We add that way, but I know exactly what you mean, okay?
Okay.
But it's
Thank you.
okay. So let's see. What should be the units you think of this? Kilograms per second or pound miles per second, okay? So that's generally something I don't have to do because you already know that pretty well. But let's see. What could be, what is the general expression for this? So let me give you the expression and then we see what happens, okay? That would be density times area times V. Okay? Let's see what will happen with the units. So what will happen with the units over here? What will be the density, the units for density? Kilograms meter cube. What will be the units for A? Okay. Meter square. What will be the units for V, which is velocity? Meters per second, no? So if you do this, what's going to happen? You see this, all those meters cancel out, no? Yeah? So and you are left with what? Kilograms per second. So if you want, let me put over here more details. So where this will be the density, A is the area, and V is the velocity. I mean, I don't want to do too much figures over here, but basically that will be the area, that is the velocity, okay, going through a certain cross section, no? Or tube. Okay, any questions so far? All right. So, this is generally the way, I mean, you and I remember the mass flow rate, but let's see. So page 72, so M equal rho AV, okay? So now, AV, if you combine it together, okay, is what is known as the volumetric flow rate. Okay? And what is the definition of the density? Mass over volume. Okay? What was the definition for specific volume? Volume over mass. So basically that means that if we use this tool, we can rewrite the volumetric flow rate as what? Sorry, the mass flow as what? AV instead of time rho divided by V, no? Because V equal 1 over rho. Yep, so we have over V. So this is the form that is most used in thermodynamics for the mass flow. Yes?
I can't tell from here, what kind of indicator are you using to differentiate between your V's?
Okay.
They look the same.
No, good question. Yeah, but if you look at it, my V over here for this is, so what I'm using is this. Let me do it by pen. It's easier. So if it's just a normal V, is velocity. Okay? If it's the V with the bar in the middle, what is that one? Volume. Okay? The lowercase v, what is that one? Specific volume. But that was a very good question, okay? Because I know those things can be confusing. Does that answer the question? Can you read it or no?
Is there like a little curly thing at the end of a lowercase v?
This is my way to do the v. Hold on. I do this way.
Okay. Yeah, now I see it. Thank you.
Depends on what one.
Is it more clear this way or? Yeah, I agree. It's all notation. Okay, so we talk about all those volumetric flow rates and so on and so on. And maybe what I can tell you here, since we have some space, recalling from previous chapter, what is H? The enthalpy. Okay, so we had capital H, but also we had the lowercase h, which would be the specific enthalpy. And what do we say? H was equal to what? That's the important part. The H was equal to the internal energy plus work done by the pressure. Only the H was equal to specific heat plus PV, no? So what's important over here to remember is that, or to understand, is that enthalpy equals internal energy plus work done by pressure. If you want, we can put, work done by pressure, okay? We should add a constant volume, but let's leave it general. Okay, so here we go now. Now we go to what's important over here. Maybe one more thing. I do everything together. Page 73. So I'm going to do the same figure as before. So for our control volume, so basically what I'm trying to put here is potential energy, okay? Give you some time to do the figure. Okay, so what is the title of the chapter? First principle of thermodynamics for open systems or control volume, no? Okay, so let me add here to this figure here. Let's say we put heat in function of time and we put work, okay? So let's say applying first principle of thermodynamics to above system. Okay? Think about what is the first principle of thermodynamics. Q plus work equal change in energy, no? Okay? But here, I'm going to add one thing because I think it's easier. Applying the first principle of thermodynamics to the above system or the equivalent energy balance. So equation is the same. The only thing is that I think it's a little bit easier to write down the equation. So energy in equal to energy generated plus energy out. Okay, I'm going to write something very quick because I'm trying to get quick to the problem. Here, E generated is equal to 0 if steady state, which is, if not 100, 99.9% of the problems you will be solving, okay? So basically it makes sense to what? The energy going inside the system is to be equal to the energy coming out of the system, no? Basically, that's what we have. Or if you want, let me write this down. Energy in equal energy out. Okay, so by looking at the figure, because remember, I never write something that comes from my mind and without giving an explanation. I try to make a figure so you know where is the equation coming from, no? All right? So if you look at this system, so what would be the system over here? Is the dotted or dashed line, no? Okay? So what type of energy is going inside that one? And we have Q dot, no? Yeah? Can we have work going inside? Or power? Yes. No? This is like the first principle of thermodynamics. But then what happened? The flow is going inside. Is the flow going to go inside with a certain velocity? Yeah. So it will come with some type of what? Of kinetic energy, no? That will be equal to what? Yeah. I don't want to write this down. That's what I'm just thinking. So we have some kinetic energy that will be let me just do this one, okay? Because what I want to do here is, let me see, I should have done at the beginning. All this is multiplied by the mass, no? So 1/2 mv squared. Now, here you see that I did, let's say the entrance is not the same height as the exit, no? Even though that time is in most cases going to be 0. So we have what? Some potential energy, no? mgh. Yeah, the m is outside. And then the flow is also coming inside, and the flow can come with what? With some internal energy. Yeah?
Is that G8 or plus GHI?
This is G C sub I. This I over here.
Oh, Z.
Yeah, Z sub I. Yeah, I know it's thick. Sorry for that, guys. So you see, this comes directly from the figure, no? Okay, and I still use the sign conventions, positive, negative. So, right. So now, what is coming out? I do the m dot sub O for m out. So what is coming out? Do we have heat or work coming out? No. Okay? But what do we have? We can have kinetic energy, potential energy, and internal energy. Not yet. Let's not do that. Okay. Oh, I knew I forgot something. Yeah, I forgot something here. Yeah, I forgot one term. So let me just rewrite the whole equation, okay? Yeah, I forgot one term. All right, so sorry for that. So let's start from 0. Maybe let me do it with the in blue. So what is energy going in? We're gonna have Q dot plus the work plus the m dot Not going to change anything here. So I'm going to do the v squared over 2 plus gz plus u plus PV input. Okay, and I will explain it now. Okay, I forgot that term over here. And this should be equal to what? To m out of v squared over 2 plus gc plus u plus PV out. Okay, so the easiest way to explain this is maybe I tried just to give a general explanation, then I give a more detailed explanation, okay? So, because the flow is moving across, all right, does that mean that the pressure in here is going to be the same than over here? Let's say you have different diameters. If you have a pipe which is this small and have a certain value of amount of water going through, you have a higher pressure than you have a much wider pipe, no? Giving the same amount of water, no? So the mass flow is the same, but the one, the little one, we have a higher pressure than the one with the thicker. Okay? So now, in the first chapter, what did we study? We studied that we know that the pressure, when it's subjected to a volume, create work. Okay? So in other words, the work done by the pressure on the inlet is creating work, and the work at the outlet is also creating work, no? Yeah? Does that make sense? Okay? So for instance, now a practical example. When you look at those engines or the aircraft, okay, the turbofans, what do they have at the front? What is the first big part of the engine? Compressor. What is the function of the compressor? Compress the air. So why do you want to compress the air? Because then you have the compressor, then you have the engine, which is like a control volume, no? Okay? But the higher the pressure you have, the more work you can produce, no? Okay? So what is the role of the compression? Is to try to transform all the kinetic energy of the flow coming in to what the ideal case would be what? To stop it to zero velocity, no? Yeah? I mean, in order to increase the pressure, you need to take the energy from somewhere, no? It will be the kinetic energy. So the role of the compressor is to slow down the flow as much as you can so you can increase the pressure. I mean, it's the same thing, you know, if somebody tries to get out of the door and you have the biggest guy on the door and just stop the door and everybody start pushing, you're just going to keep increasing the pressure, no? Okay? But if you start going out, then the pressure is going to go down. All right? So the ideal case is to be able to do all that pressure there so that then once you move into the volume, you can produce as much work as possible with the P dV, no? Let's say the pressure is constant, the volume is constant, you do PV. All right? So basically, that's the explanation for this term over here. So we have one on the inlet, one on the outside. Okay? So maybe now I'm going to put a bit too much information. All right, so we have that equation. And I'm going to say recalling the definition or expression for enthalpy. So what is enthalpy? Internal energy plus PV, no? Okay? So if we look at this equation, what is this term over here? H, no? What would be this term over here? H. So we can rewrite the equation. So the equation becomes heat transfer plus power plus mhe plus 1/2 m v squared plus mgze equal to m dot okay, I forgot here to put the input. Sorry for that. Input out h out plus 1/2 m dot out p out dot plus okay, I'm going to simplify this very quick. So what do we know? So let's say where we say that the amount of mass going in need to be equal to what? To the mass coming out, and let's just call this one m dot, okay? Okay. And in most cases, change in potential energy is equal to 0, and the change in kinetic energy is equal to 0, as you have seen in the problems, no? So what does that mean? That all those terms over here, the m dot v approximate 0, and the m g z are 0, no? Okay? So let me just, this is like an enter, it's not an L, okay? So it's like the enter key. So this equation now is going to reduce to what? Q plus work equal to m dot what? H outside minus H inside. Yes.
What happened to internal energy?
Where is the internal energy included over here?
That U?
That's U, but what is H?
Oh, it's the whole thing.
No, but that's a very good question, because that's the whole thing. Remember, and I think the only reason why they came up with the term enthalpy is to solve this type of problem, because what is the enthalpy? Is the internal energy plus the work done by the pressure. Okay, so that's an excellent question, because we don't really need the H. We could keep the U and the PV, no, and calculate it. All right. But basically, at the end, so this equation looks a lot like the first principle of thermodynamics, no? So heat plus work equal change in energy. All right. So here, what's important is that when we're dealing with closed system, we're dealing in most cases with what? With internal energy, U, and then with the PV. We keep those two terms separate. Okay? In open systems or control volume, those terms always go together. Okay? So if that is the case, if you remember, H is kind of proportional to what? Remember, U, I told you, that's very important. U is related to which one of the coefficients? Specific heat coefficient, we had C, we had C sub V and C sub P, no? So something now you need to kind of remember, even though you don't understand it, is that C sub V is related to what? The internal energy or to the enthalpy? So C sub V is related to the internal energy. C sub P is the one that is related to the enthalpy. Okay? So let me see. So we have this one is the Cp delta T. So what I want you to here make sure is that when you see H, think about C sub P. Okay? And when you think about U, internal energy, think about C sub V. So didn't we do that stuff? Conduction, trying to find out. Nine, okay, 8. Okay, 8. Yeah, I think we should have done it at the time. Yeah, here it is. When we did, remember this figure about the Gay-Lussac experiment? Okay? Said internal energy was equal to some coefficient, C sub V, that means how much heat can that substance absorb or retain, no? Okay? So this is the original one. And then I think I probably did the derivation that, so you see this is C sub V, internal energy is related to C sub V. C sub V is internal energy, okay, that's not important. I think then I did, okay, what happened for if you define the enthalpy as being equal to U plus PV and rewrite the first principle of thermodynamics in function of H, we had that dH was equal to Cp delta T, no? All right, so that's important thing. And here, this is a specific heat at constant pressure. All right, so this is what, let's say, page 52. So I can put it over here. Page 52. Class notes. Okay, I'm gonna do just one more thing. Okay, why I don't have a clear explanation why they had to come up with the term enthalpy. Okay, personally I don't really know, but if you think about the engine of an aircraft, what are the different components you have on the engine of an aircraft? You have here so you have air coming with certain velocity, no? Yeah? So if you want with some kinetic energy, it's going to get into the compressor. We'll do a problem next time. Then ideally at the end of the compressor, what's gonna happen? The pressure is gonna be maximum and the velocity should be 0. So you transform all the kinetic energy into pressure, no? Okay? Now, what do you have in the middle? This will be, if you want, your control volume, no? Yep. Okay, so this will be your control volume. So into the control volume, you have the work done by the pressure, because this is constant V, so P max times V. All right, it expands over here if you want. But then what do you do inside this? But what do you do when you inject fuel into this? I mean, this is, let's say, fuel with the spark. What do you do over here? You inject fuel, you spark it. What's happening? It goes boom. So what happened here? Did I touch something? What happened? I mean, this stuff just crashed by itself. So anyway, when you put the fuel, you put the spark, what are you doing inside the system? You are adding internal energy, no? Yeah, under form of heat if you want. So now you have all that energy inside. You have transformed all the velocity of the flow, the kinetic energy that's coming inside the engine. You have transformed all that stuff into a very high pressure. Okay? Now you can use all that high pressure you have created into creating work into a constant volume. Okay? In addition to that, you add energy through internal energy by burning fuel. So now you have a bunch of energy inside here, no? Now, what do you want to happen? You want the velocity to exit, no? At a much higher velocity than it came in, no? So what is the mechanical device which is going to do that? What is this over here? Compressor, and this will be the turbine. Okay, so compressor, turbine. So what is the role of the turbine now? Turbine is the one to transform all the energy over here into higher velocity, and if you want, it also create work, and is the one which will be driving the compressor. So really, if you want to do the design of an engine, you need to think about what? You want to have a high pressure and high internal energy, no? So that means you want to have a high enthalpy, no? So I think that's the only reason I can think logical why they came up with the term enthalpy. Because when you do the design of an engine, what you want to get is a high enthalpy. Instead of repeating every single time, I want a high internal energy plus high pressure, no? You want a high enthalpy. Which means what? You want to have a high pressure plus a large amount of internal energy. Okay? So now I'll give you back the exams.